log base e of x, which we're not going to write like that. We're going to write it as ln of x. ln of x is how we write it. So, I didn't mean to write that. So log base e, see, log base a of a to the x is x, if these two are a's. So log base e of e to the x is also x. But instead of writing it like this, we're going to say ln of e to the x. That's an n. It's just understood that it's really log base e there. This answer is x. This is the exponent you put on e to get e to the x. It's x. So you could graph this by looking at like this again and plugging a number here. Like if you plug a 1 here, that mean the answer is 1. Now remember, that's the x coordinate right there. This is the y coordinate. So you're plugging in e to the 1, e, and you're getting 1 back. If you put a 0 right there, that would be, and you get 0 back, the y coordinate is 0, and this would be e to the 0 would be 1. Same as the other one, but anyway, that's a graph. Okay? Hopefully that was enough because I did a lot of those. And on this paper, like I said, that I plan on showing you on Canvas, hopefully you can read it. I scanned it. But here's the natural log. I call it p of x here. P of x equals ln of x. It means log base e of x. Again, it's just the base is e. So it's really a is bigger than 1. It's e. It's just one specific number. Here, this stands for all graphs. A can be anything bigger than 0, not equal to 1. This is all the graphs with a bigger than 1. This is one particular one. I pick a to be a number, e. I know it's still a letter, but e is a number in mathematics. It's about 2.71828, that irrational number I showed you. That's like log base 2 of x, really, in a way. The specific number is picked. So this is a specific one, but e is bigger than 1, so you're going to get this shape, just like this one. Just like this one, same shape. And, even from this one, you say 1 over 0, a1, e1, etc. I just graphed it, so it looks like that. Domain, 0 to infinity. Range, negative infinity to infinity. Y equals ln of x is equivalent to, see, this ln of x is the exponent you put on e to get y. So e to the y equals x. All right? And, all this stuff in the middle is the same here. These two, same thing. The x-intercept here is 1, 0, smooth, continuous, 1 to 1, vertical asymptote here, which is x equals 0, or the y-axis. It's increasing, it's concave down. As x goes to infinity to the right, ln of x goes to infinity, the y-coordinate goes up, but graph goes up. As x goes to 0 from the right side, like this, I'm moving this way, ln of x, the y-coordinate, goes to negative infinity. The graph shoots down as it approaches the y-axis. Okay. And this stuff will be covered in a later chapter, but I've already shown you these. So let me just go over them again. Look, this is at the bottom of this page. If these two are a's, you get x. Remember, log base a of x, this right here, that's the exponent you put on a to get x. So if you put that exponent on a, you get x. But this is only true for x greater than 0. Remember, you can't take the log of 0 or a negative number, so that x must be positive. See, if these two a's, we've used this a bunch of times. If these are both a's, you get x. Remember what this left side is. This is the exponent. This whole thing is equal to the exponent. You put on a, the base, to get a to the x. What exponent would you put on a to get a to the x? You'd put x there. Now, this is true for all real numbers, because you can raise a to any power. These two are the same as these, but just for the a, I put the e in. It's just one particular number. So this one, you put an e here and here, it turns into this. See, e to the log base e of x, but we say e to the ln of x. Remember, ln of x is the exponent. You put on e to get x. So if you put it on e, you get x. And again, this is only true for x greater than 0. If you convert this one to base e, you'd say log base e of e to the x, ln of e to the x equals x. Remember, this side is the exponent. You put on e to get e to the x, x. This is true for all real numbers again. But anyway, we'll go over those again. But there's a bunch of stuff. What else? Well, let me show you how to use a calculator a little bit, because you should know how. But let's say, I just graphed, I don't know where to put it now, but I just graphed, ln of x right here. Notice in this table, I plugged in powers of e, really, because I could get the answer without a calculator, because ln of e to the something equals the something. But I don't, as long as I put a number bigger than 0 in, I'm fine. I can find the ln of, let's say, 2. Suppose I plug in a 2. I want the y coordinate. So I want, over on this side is going to be ln of 2, but I don't know what that is in decimal form. That's the answer. So let's see what it is. If you have a scientific calculator, which you're supposed to have, you'll see a button with ln on it. ln. Now this is, like I showed you the other day, this is a graphing calculator, but it works pretty much the same way probably if it's a modern calculator. So ln, I got to turn it on first. Let's clear that. So ln, and then I'm going to plug the 2 in, close the parentheses, enter. It's about 0.69. So ln of 2, that, which is about 0.69. So 2 to the right, up 0.69. ln of 2. 2 ln of 2 is on this graph, but the ln of 2 is approximately 0.69. And notice E is bigger than that. See, this is farther to the right. This is 2. This is E is about 2.7. You're all the way up at 1. It's higher than this one, which is supposed to be. But see, you can plug any number you want into the log function as long as it's in the domain. Now notice, when I do ln of a negative number, it may come out weird, but let's see, ln of negative 2, watch what it looks like. See, it says error. Some calculators may kind of give you an answer, but understand they're really dealing in the complex number system. So don't worry about it. You can't take a log of a negative number. Watch log of 0. ln of 0. See, again, error domain, because it's not in the domain. So you'll get an error of some sort with log of 0. Any positive number, you're fine, though. Notice, if I take ln of e, it'll be 1. Now watch. ln of, whoops, I don't need that. ln, what am I doing? Okay, ln, hit that, and now I'm going to enter e. But to enter e, remember it's above the log function. So second function, e, then it asks for an exponent, so I'm just going to make it 1, e to the 1, close the parentheses for that exponent, close the parentheses again, enter, 1. If I took ln of e squared, I'd get 2. If I put in ln of e to the negative 5, I get negative 5. So you can try that on your calculator. Your calculator also has log base 10. Here it is right here. And above it is 10 to the x. So if you want to raise something to a power of 10, you can do 10 caret 3, let's say. You can do it like that. That's 1,000. Or you could say second function, hit the log button, because 10 to the power is already written there, and then enter the 3, and I get 1,000 that way too. But the log button is here. So suppose I want the log of something. Now look, for example, this is the common log, base 10. Here, let's say log of 1,000. Now shouldn't that be 3? Because remember, this is base 10. That's 10 to the third. So let's take a log of 1,000. So hit the log button, enter 1,000, close parentheses, enter 3. See, that's the exponent you put on 10 to get 1,000, because this is base 10, this log here. Notice your calculator doesn't have log base 2 or log base 1/2. So how do you deal with those? I'll show you that later on. You got to use these logs. I'll show you a way. It's called change of base law, but there's a formula that does it for you. I'll show that to you eventually. So we can find the log of any number, but you got to, if it's not log base 10 or log base e, you got to use a formula involving these, or you use these. But we'll do that later. If you want the log, say I want the log of, let's say, 80. Now let's even guess where it might be. Look, this is base 10, right? What's the log base 10 of 10? Isn't it 1? What's the log base 10 of 10 squared, which is 100? Isn't it 2? 80 is between 1 and 2. This should be between 1 and 2. Let's find out what it is. So log of, whoop, I hit the wrong one. Clear. Okay, log of 80. 1.9 approximately. And let's go further. See here's what this means too. I just found the exponent. Now this is approximately, it's not exact. This is the exponent you put on 10. So 10 to the 1.9 should be approximately 80. This is the exponent you put on 10 to get 80. Watch, 10 to the 1.9, it ought to be close. 10 with an exponent of 1.9. See, 79.4. See, really, log of 80 is 1.903, a semi-rational number. But I cut off this part of the, the decimal. I rounded it for one decimal place, so I lost. It's really a little bit bigger than 1.9. If I punched all those numbers into my calculator, it probably would come up 80, even though that's not the exact answer. That's just all my calculator can handle. It really goes on forever and never terminates, never repeats. Even ln. See we did ln of 10. So log base e of 10. Let's see what that is. ln of 10. See, it's about 2.302, so it's about 2.3. So approximately 2.3. That means e with an exponent of 2.3 should be close to 10, approximately 10. Now, it's not going to be 10 because, once again, I truncated. I cut it off after 3, so it's really a little bit bigger than that. So I'm going to get 9 point something, but it ought to be kind of close. Let's see. So second function, hit the ln button. That's e to a power. And then I'm going to substitute in that answer that I got, which was 2.3 approximately. So 2.3. Close the parentheses, enter. See, I got 9.97. So close. But anyway, you should know how to use your calculator to take logs and to raise the powers. Okay? All right. So I did some calculator stuff. Let's see. So, all right, let's solve some simple type log equations. Now, again, there's a section later on, 11 point something. I don't know. What's this? This is 11.3, so it's probably 11.5, but I don't think it's 11.4. And we'll learn how to solve exponential and logarithmic equations, a whole bunch of different types of equations. They, can't solve everything, but more complicated ones than these. Remember, we learned how to solve some exponential equations, but they were a certain type where we could write both sides with the same base. You can't always do that. And we'll learn how to solve different types of exponential equations than the ones we've already done, and different types of log equations than these later on. But right now, let's take a look at this. Let's suppose we're supposed to solve these log equations. Now, a way to solve this is to, I want to get that at x. So I want to get rid of this log here. And one way is to write it, when it's just like this. It can't be too complicated. I'll show you some more complicated ones later on. But this one we can write in exponential form, for example. Remember, this whole thing, which equals 2, is the exponent you put on 3 to get 4x minus 7. So that means 3 to the second power equals 4x minus 7. Whoops. So I rewrote the problem. That means the same thing, just written in exponential form. So 4x minus 7, I don't know why I can't write a 7. 4x minus 7 equals 9. Add 7 to both sides. 4x equals 16. Divide both sides by 4. X equals 4. Now, I want you to be careful when you solve log equations. This one's okay, but you got to be careful. Just like when you solve log equations, sometimes you get extraneous solutions, like we did with rational equations and like we did with radical equations. You got to make sure that when you plug the number back in, you're not taking the log of 0 or a negative number. You can check it by plugging it in all the way, and you're just figuring out both sides. But you better not be taking the log of 0 or a negative number. If you are, you got to throw that answer away. It's an extraneous solution. So a check is, I'm going to require a check for logs. So let's check it. Now when you plug it in, look, you have log base 3. I'm going to put the 4 right there. So it's 4 times 4 minus 7. That's the argument of the log. That's where we're plugging the log. And the question is, does it equal 2? 4 times 4 is 16. Minus 7 is 9, so that's a 9. See, that's a positive number. I know I'm okay. Now, I'm going to keep going, but right now I know I'm okay, that answer is okay. But log base 3 of 9, remember 9 is 3 squared. I'll write it like this time. Oh, that's 2. So 2 equals 2. Checks out. I know this side's 2. I'm not going to. Here's another way of doing that problem. Here's another way. Here, let me get another piece of paper, I guess. Now, this is a little fancier, but you probably want to do it this way. But you could do this also. Now, remember, this is true. I already showed you this, a couple of times, but, here it was, if you recall, even on this piece of paper that I told you I'll put on Canvas somehow. But when you have something that looks like this, a to the log base a of x, you get x. Now, we've done that several times, but that's true. So, because remember that this is the exponent you put on a to get x. So if you put it on a, you get x. Okay, so this is equal to x. But these two undo each other. Okay, so since this is equal to this, I could say then 3 to this power with this exponent must equal 3 squared. Since these two are equal, 3 to that power must equal to 3 to that power, because I'm really raising 3 to the same power. Now notice these two undo each other. Remember, that's this. See, when you have this, you just get that right there. This is the exponent you put on 3 to get 4x minus 7. You put it on 3, this side turns out to be 4x minus 7. That's really two inverse functions undoing each other. Equals 9, and we're right back to that. We already solved it over here, 4. This one, again, you could write it in exponential form. See, this is really log base e on this side of x. That's really what that is. So e to the 4th power equals x. X equals e to the 4th power. Done. The only other thing you could do is approximate e to the 4th by punching it in a calculator, but that's the answer. You could also use this again. See, if there's an e here, e to the ln of x, undo each other, you get x. This is the exponent you put on e to get x. So if you put it on e, you get x. But if remember, this is log base e. These two undo each other, you get that. So since these two are equal to each other, you could say e to the power of ln of x must equal e to the 4th. Now remember, these two undo each other. This side is x. So x equals e to the 4th. You could do it like that. Here's one. This one, let's write it like this. Let's use, the easiest way is just write them in exponential form for problems like this. But see, this means this is the exponent you put on x to get the 64. This is the exponent you put on the base x to get 64. So x squared equals 64. So x equals, take a square root of both sides. I'm assuming you can do that, plus or minus 8. And by the way, you're supposed to check the answers. Even down here, e to the 4th is positive, so that's okay. See, ln of e to the 4th is 4. This one you got to check. So let's check them. The 8's okay. Log base 8 of 64 is indeed 2. Now, as long as it's, see, this right here, as long as it's positive and not 1, you're okay. Because remember, that can't be positive, it can't be 1. I mean, can't be negative, can't be 0. It has to be greater than 0, not equal to 1. The 8's okay. Because look, 64 could be written as 8 squared, and it would work out. Log base 8 of 8 squared is 2. But this has no meaning. If I pick the negative 8, look at the negative 8 one. We're not allowed to have this equal to a negative number, or 0, or 1. Why? Because that's it. We got this function from the exponential function where the base was restricted. And that's the base of the exponential function, when it's the inverse. This has to be greater than 0, not equal to 1. So throw the negative 8 away. The negative 8, toss it. You just get x equals 8. That's the answer. Okay? All right. You could also, if you wanted to, you don't have to do this. This might be more complicated, but you could say, use this again. Even though there's an x there, see? X, see, that's the base. So x to the log base x of 64, x with that power must equal x squared. Remember, these two undo each other. Log base x of 64 is the exponent you put on x to get 64. Well, you put it on x, this side's 64. So you just get this again and solve that. Here's another one. Notice there's no base written. So it's understood to be a 10. The easiest way, again, is to write it in exponential form. Remember, this is the exponent you put on 10 to get negative 1. So 10 to the negative 1 equals that 2x minus 3. Or no, this is the exponent you put on 10. In other words, a negative 1 is the exponent you put on 10 to get the 2x minus 3. I think I said that wrong. Don't even remember what I said now. But 10 to the negative 1 equals 2x minus 3. So 2x minus 3 equals 10 to the negative 1. That's 1/10. Now you can multiply both sides by 10 if you want. Or why don't we just add 3 to both sides? So 2x equals 3 plus 1/10. That's 3 and 1/10. I'll just write it like that, or 31/10. Multiply both sides by 1/2. So you have 2x equals 31 over 10, multiplied by 1/2 on this side, or divide by 2, multiplied by 1/2 over here. 1/2 times 2 is 1, so x equals, what's that, 31 over 20. Now you can write it as a mixed number or a decimal too, but that's the answer. And check it. Now remember, really all you have to do is make sure that this is, you got to make sure, depending on where the variable is, but if it's in the argument of the log, you got to, when you plug it in, you got to get a positive number here. You can't get 0 or negative. If the x is down here, you got to make sure that it's, positive. It can't be negative or 0 or 1. But let's just, if you put 31 over 20 there, you'd have 2 times 31 over 20 minus 3 for this. 2 goes into 20 10 times. That's 31 over 10. That's 3 and 1/10. This is 1/10. It's positive. That answer is okay. Now you can plug it in and check the whole thing, but that's all you really have to do there. Okay? Anyway, that was kind of quickly, but hopefully that helps you solve. We're going to learn how to solve more types of log equations when I cover some other sections. Now I want to do one example. I have a loudness thing here that I stole from the book. Let me see if I can, where are we at here? I think I did most of the stuff in the book, so you should be, look at the book, and you're supposed to look at the book and do all your homework and MyMathLab and all that kind of stuff anyway. But yeah, on page 815, there's a definition of loudness. It says the loudness L in decibels, probably a lot of you heard of decibels, of a sound of intensity X in watts per meter squared is given by this formula. If I gave you this problem, I'd give that formula or let you get it, the formula. You don't have to memorize that, obviously. Sometimes they have formulas in logs. One reason they might do that is that the domain has such a wide range of values. See, I Googled this, and I saw one webpage that said, like, 10 to the negative 12th, see it right there? That's the threshold of the average person's hearing, I guess. Below 10 to the negative 10 to the negative 12th watts per meter squared, you can't hear something below that. Now notice, if that was in decimal form, that's decimal point. 0.0000, 11 zeros 1. So really, really, really close to 0. And 10 to the 4th, when you get up about there, you're busting your eardrums. I think a jet engine right next to it is like 10 to the 3rd watts per meter squared or something. But 10 to the 4th will blow your eardrums out. So anyway. But that's a wide range. Look, all the way from 0.00000, 11 zeros and a 1, all the way up to 10 to the 4th, a 1 with 4 zeros. When you take a log of something, you're really dealing with exponents. So, if you just took a log of these, you'd go from negative 12 to 4. See, log base 10 of 10 to the negative 12 is negative 12. Log of 10 to the 4th is 4. So sometimes you take a log to kind of get a nicer range of answers. But anyway. And by the way, 10 to the negative 12 turns into 10 decibels. So 10 decibels is kind of the threshold of hearing. And if you have 160 decibels, it blows your eardrums out, basically. Okay? So, let's see. Here's a problem. There's one in the book, but I have another one here. It says, I'm just going to read it. A dripping faucet has an intensity level of 10 to the 9th watts per meter squared. This is a dripping faucet, like in your bathroom, drip, drip. But that's the sound intensity. How many decibels are there in the sound of a dripping faucet? Convert that to decibels. Remember, the L is in decibels. So L in decibels equals 10. This is the X. This is the sound intensity. So we're going to plug that X in here. So we have 10 times log, the common log. Remember, there's a base 10 here, which is not written, of X, which we're going to plug in right there. I don't know if they have parentheses, I guess, but we're going to plug in 10 to the negative 9th right there over 10 to the negative 12th. So notice what I did. They gave me the watts per meter squared, so I plugged it into the formula. Equals. So the loudness in decibels is 10 times the log, the common log, base 10. Notice this. 10 to the negative 9th over 10 to the negative 12th. That's supposed to be a 12. 10 to the negative 9th over 10 to the negative 12th is equal to 10 to the negative 9th minus a negative 12. Remember, you subtract the exponents. That's negative 9 plus 12. That's 10 to the 3rd. So loudness is 10 times log base 10, common log, of 10 to the 3rd. This you should be able to, just look at and tell. See, the base is 10, this is 10. Remember, when these two numbers are the same, you get the exponent. Log base 10 of 10 to the 3rd is the exponent you put on 10 to get 10 to the 3rd. That's 3. That's 3. So this is 10 times 3, 30 decibels. dB is this decibel symbol. But anyway, that's section 11.3. That's good enough, I guess.